So welcome all. Today we are going to see something about runtime environment. Actually, we understand that we are thinking about a compiler which will ultimately have a grammar. With this grammar, we will have some semantic actions. When a particular production is reducing, you will do something. Maybe in those periods you will come through some statements, some variables, and certain things where you will have to interact with the environment. Environment means you will have to interact with the hardware kind of things, operating systems, and these things. Now the thing is, basically for these variables, statements, or whatever we have, we will have to take care of few concepts like that we have seen, names, scopes, bindings, and data types, suppose operators, procedures. So now you write it. So we will have to take the care of some certain things like names, I should say scopes, operators, bindings, runtime binding or compile time bindings. You will think about data types, other thing is suppose you will have some parameters of procedures you will have, you will have this thing, parameters of the procedures. Suppose flow of control constructs. So we will have several things to take care of. So now this compiler must cooperate with the operating system and other system softwares to support these concepts, to realize these concepts on the target machine. So for doing this, what the compiler does, it creates a runtime environment and manages it. It assumes that its target program are being executed in this runtime environment. Okay, so the environment actually deals with a variety of issues. Maybe suppose one thing you will see is issues being addressed, right? What are these things? You will see it addresses some issues like allocation of storage. I should say how it looks, that's also. So layout and allocation. Layout and allocation of suppose storage locations. Now suppose the mechanism that will be used by the target program to access the variables. Suppose how the variables will be accessed. Right. They will also take care of those linkage between procedures. They will take care of how the parameters are being passed. They will take care of the interfaces between these things, suppose hardware and these operating system. Suppose interfaces between actually between this compiler and operating system, OS, I should say, interfaces to the operating system, IO device, and maybe other system softwares. So these are certain issues this runtime environment will take care of. So basically what we come here is the allocation of storage locations, and how these basically we have to understand how these variables and other related informations are stored in the memory and how they are retrieved, right? So basically let us start with storage allocation. Let me say what is storage, let me say organization. So what happens with the memory? Suppose this is your RAM, this is your memory. So you will segment this memory in certain parts. You will have a code segment. If you have written programs in assembly language, you may remember how there are certain segments in memory. You would have used code segment and data segments frequently, right? So here you should understand that we have a code segment, means I should say a part of memory. We are calling it code segment, right? There will be a static, other will be heap memory, some other free memory if at all needed. Some memory can be extended or some memory can be reduced. Okay, and then there will be a stack. Basically when you have to understand what happens, this stack grows in this direction and heap grows in this direction. So this is a part where we are calling it as a free memory. So if stack needs, it can use this part of memory, or if heap needs, this can use this part of memory. Now what we have to understand here, these part of memory, when they are used and for what purpose, right? So suppose what happens is, so let us assume this runtime storage comes in blocks of contiguous bytes. So 1 byte is the smallest unit of addressable memory, and a byte is 8 bits and 4 byte may be considered as one word. Okay, so there can be multi-byte objects for which contiguous memory will be needed. One thing that we can understand is there are different data types. We would have heard about int, float, character and others. This can be considered as elementary data type, है ना? Elementary data type, which are suppose int, float and character like this. Other can be such data types which you can say as aggregate types, है ना? Like you will have array, you will have suppose any structure you have. So what I am saying is for elementary data types, int, float, whatever, you can determine the number of bytes, maybe 4 byte, 8 byte and so on. So there we can say it is integer number of bytes. For array and structures, nothing is predetermined, but still a large enough memory will be required to hold all the components of these aggregate types, right? So what happens, the storage layout of data objects actually influence how the data is being stored. Actually I should say how the data is being stored influence how they will be addressed. So actually we are assuming that the memory is coming in a chunk, right? So if we are saying that one word is of 4 bytes or suppose 4 bytes, so what we are thinking is we will assign the memory according to the requirement. Suppose you are having an integer of 4 bytes, so you will try to assign an address which is divisible by 4. You will start either from 0 or 4 and so on. You will not start from 3. So that is something that we usually do. Now so this can be we can call it aligned, right? So if it is array is divisible by 10, so after 10 words we are addressing it according to the way it is divisible by 10 kind of thing, right? Let be, that is the way. Other thing can be, suppose for something you are assigning enough memory. Suppose you have a requirement of 10 characters, so 10 memory locations, and you are allocating suppose 12 bytes. Just for proper alignment, that we usually have suppose 4 byte addressing, so we don't want to use just from 0 to 11 here, you know? Actually 0 to 10 we want to use it to 11, you know? So that what will happen means, what I am saying is just not the 10 bytes, since it is a 4 byte addressable memory, so we want to assign 12 bytes, right? So in that case, if only 10 bytes are being used, then this portion, the 2 bytes will be padded by 0. This will be called as padding, where the remaining portion of this memory will be assigned some 0 values or kind of things. Now this is padding. However, in certain cases when you will not have enough memory, in that case this can be packed also. This can be packed, where although it was 12 byte addressable, means 4 byte addressable memory, but since we have a memory constraint and we need the memory, in that case we are packing it in 10 bytes only, and we are using this remaining portion. we will call it packed. Now the other thing we have to understand about code static, heap and stack. So suppose what happens, this is our compiler, it generates the target code. So when it generates a target code, the target code is fixed, right? The target code is fixed at compile time. So the compiler can place the executable this target code in a statically determined area. We will call it as this code segment. So whatever the code was there, target code generated by the compiler, it will be placed here in code segment. So code segment, you can say it is in lower end, is in the lower end of the memory, right? So along with this code, you can have size of some program data objects like global constructs, data generated by the compiler, maybe support to garbage collection, some information which will be known in the compile time, that can be placed where? In this static location. Okay. So certain variables also you understand which are created in compile time only. The memory is allocated in compile time only we need. So whatever these kind of data are generated at compile time, they are stored in a static part of the memory. Now what happens? To minimize the utilization of space at runtime, these two other areas, heap and stack, are used. Okay. So you can see heap grows in this direction and stack grows in this direction. So these are actually used in runtime. So they are these areas are, you can say, they are dynamic. Let me write. They can be considered as dynamic. Their size can change since they can grow according to the need of the memory. And a stack will be used to store the data structure called, I should say, activation. Activation records. Okay. These activation records are actually the records which are created at the time of function calls. When there is a function call, there is a running procedure which has certain information, maybe at which position currently it is executing, what are the defined variables being used, what are their other semantic informations. All these information will be considered in a record. We will call it activation record, and this activation record will be pushed in the stack. This activation record will be pushed in the stack and a new function can be called and it will start executing. When this function will terminate, then again it will, according to our semantic information, what we have to do after its reduction. So usually what happens after return, when there is a return statement here, the activation record is fetched, I should say popped from the stack memory and loaded accordingly, and the next statement which was to be executed in this function starts executing. So this is how this stack memory actually is used. So usually what happens, as I told, stack grows towards the lower memory and heap will grow towards the higher memory. It happens, but for our understanding we can say that both are growing. We can use a growing direction for both of them. So now these are few things that we had to see in this storage allocation and these things. So we have seen these things from a Holman book, and for more detail this Holman book can be referred. Now we will see some more things about registered allocation in next video. Thank you.